A very good morning to all of you. We have been discussing electromagnetic induction, and today what I want to discuss is a very important application of electromagnetic induction in the generation of electricity. So, we will be discussing an alternating current generator. Or an AC generator. Okay, so let us recall that according to Faraday's law of induction, whenever there is a changing magnetic flux through a closed loop, then there is an induced EMF generated in that closed loop, and that induced EMF is given by the rate of change of flux, rate of change of magnetic flux through that loop, and the direction of the induced EMF is determined by the Lenz's law. So, let us recall the induced EMF is equal to minus d phi b by dt, where phi b is the magnetic flux and phi b we are defined as integral b dot dA. So, that is the magnetic flux, and whenever this flux changes with time, then there is an induced EMF in the circuit. Now, if I take a region, suppose I take a small region of space where B is uniform, then phi B becomes actually B dot A, and this is equal to B times A times cos theta, where suppose I could have a circuit like this. The magnetic field is pointing like this, and I define the area vector like this, and this is theta. So, remember, I must consistently use the EMF generation, calculation of EMF on the left hand side with the magnetic flux which I am defining on the right hand side, because the area I am defining like this, the induced EMF calculation, the loop calculation must be like this. EMF, which is integral E dot dl, must be integrated in this direction, so that I am in the right handed screw notation. So, the magnetic flux passing through this loop is proportional to the magnetic field, depends on the area of the loop and the angle between the area vector and the magnetic field. If any of these changes, if any of these quantities change, then there is a change in the magnetic flux, and that change in magnetic flux will induce an EMF. So, we could have, for example, the magnetic field itself changing with time, and that is what happens when you have a solenoid and you change the current in the solenoid, then you are changing the magnetic field within the solenoid, and so that induces an EMF. You could change the area keeping other two terms constant. You can change the area, for example, when we had calculated the motional EMF, where we had a conductor moving on another conductor, we showed that there is an area which is changing with time, and that area change with time creates a changing flux with time, and that creates an induced EMF. It is also possible that both magnetic field and area remain constant, the magnitude of area remains constant, but this angle theta changes. So, if you have a coil which is rotating, then because the area vector is rotating with time, the cos theta term will change with time, and that will induce a change of a magnetic flux with time, and that magnetic flux change will generate an EMF. So, this is a principle that is used in the AC generator. So, let me draw the generator, which looks something like this here. So, I have a magnet, a permanent magnet, one pole here, there is another pole on this side. So, let me assume this is the north and this is the south. So, the magnetic field lines are pointing from left to right. Now, in this what I have is a coil. Let me draw the coil like this. So, let me draw the position which is one particular orientation. So, there is a coil which is placed inside the magnetic field, and what I do is I connect these two ends of the coil into what are called as rings. So, here I have a ring, and here this is connected to one ring here, and this is connected to another ring on this side. And what I do is I make an arrangement in which I can rotate the coil with respect to the magnetic field as a function of time. So, this is the construction. So, I have a pair of pole pieces here. This is a strong magnetic field between the two pole pieces, a uniform horizontally directed magnetic field. I have a coil which is connected to two rings here. So, and this coil can rotate with respect to the magnetic field, and these two contact points are such that they are always in contact with these two rings, and what I do is I take out the output from these 2 points and look at the potential difference between these 2 points as a function of time. So, when the coil rotates, the area vector rotates. The rotation of the area vector implies that there is a change in theta, cos theta, which I wrote before. As theta changes with time, the magnetic flux passing through this loop changes with time, and the changing magnetic flux will induce an EMF which will develop a potential difference across these 2 points in the outside circuit. So, this potential difference I can use to drive current through an external circuit. So, let me try to illustrate what will happen through a slide here. So, let me show that this is the slide. So, these are the 2 points here, P is here and Q is here. So, I have purposely drawn one as a red line and the other as a blue line. So, I show this too, and so what happens is at some instant of time the coil is like this. So, let me assume the magnetic field is horizontal, and let me assume the magnetic field is coming out of this paper. So, when I rotate this with respect to time, you see that the area vector is changing, and after some time the coil becomes horizontal. When the coil becomes horizontal, there is no magnetic field passing through the coil and the flux becomes 0, and then it rotates further and becomes like this, and again the flux becomes maximum because cos theta becomes 0, theta becomes 0 and cos theta becomes 1, and then if I rotate further, it again becomes horizontal and the flux becomes 0, and here the flux becomes maximum. So, what is happening is the flux is maximum because the coil is perpendicular to the magnetic field. So, B dot A is B A, cos theta is 1. Then after quarter cycle, when it becomes horizontal, cos theta becomes 0. So, there is no flux because area vector is above or area vector is below, and there is a magnetic field which is perpendicular to the area vector. So, the dot product is 0. After another quarter cycle, the coil becomes again vertical with a maximum magnetic flux, and then the coil becomes horizontal with 0 flux and a maximum flux. So, what is going to happen is the flux through this coil is going to change with time, and that will induce an EMF in the coil. Now, there is something to be noted here. So, let me assume that the magnetic field is coming out of this paper. So, towards this side. So, the flux is, so if I consider this loop to be in this direction, because the, so okay, so if the flux is like this, if the area vector is up, please remember the integral has to be done like this. So, when I rotate this, the flux is decreasing with time, the flux is positive and decreasing with time. So, d phi by dt is negative, and so EMF is positive, and as it rotates, so here for example, let me assume that the EMF is such that the current is flowing like this from blue side to the red side. After half a cycle, you see here the red side becomes below and the blue side becomes up. The current is now flowing from red to blue. Please note, half a cycle before the current was so this is the EMF is like this for example. So, initially this was at a higher potential compared to this when it was rotating like this, Q was at a higher potential than P, then it rotates through half a cycle. Now, P has come below Q, so P is at a higher potential than Q. So, what you can see is the potential difference between P and Q will oscillate with time, starting from this position to this position, and it will continuously change with time, generating what is called as an alternating current. So, one thing to remember here is because I am rotating the coil, the area is changing, area vector is rotating, and so cos theta is changing, and as cos theta changes, the magnetic flux changes, and because of the reversal of the orientation of the coil, the EMF will reverse itself. So, let me draw a figure here just to explain. So, in this figure what is going to happen is that initially for some time this is at a higher potential compared to this, and then after half a cycle this will be at a higher potential corresponding to this. So, the EMF, the potential difference will keep on reversing itself. So, let me assume that this rotation is at a angular frequency omega, omega is the angular frequency of rotation. So, let me try to draw what happens as a function of time. So, here is the diagram. So, let me draw this as a function of time. Let me draw the flux, magnetic flux. So, let me start by looking at the coil. So, let me start by assuming that the coil is perpendicular to the magnetic field. So, the flux is maximum, the flux will go through one full cycle in a certain time. So, this is the time for one full cycle of revolution of the coil. Now, at this position the coil was like this, at this position the coil is like this, at this position again the coil is like this, at this position the coil is horizontal, and at this position the coil has become again vertical, and the coil is rotating like this. So, if I were to draw an area vector, here the area vector was pointing like this, here the area vector is pointing downward, here the area vector is pointing left, here the area vector is pointing up, and here the area vector is pointing to the right. So, you see this arrow is rotating as a function of time. It was pointing like this, after some time it becomes like this, then it becomes like this, then it goes up, and then it becomes. So, this cycle is repeated again and again, and the frequency of oscillation, the frequency of rotation I have said as omega, and so the flux is changing with time. Now, if I want to draw on the same figure an EMF generated, please remember EMF is proportional to minus d phi by dt. So, d phi by dt is the slope of this curve, minus d phi by dt is minus the slope of this curve. So, let me see in this region. So, in this region d phi by dt is less than 0 till this point, and then here d phi by dt is greater than 0. In this half of the cycle d phi by dt is less than 0 because the slope you can see of this curve as a function of time is negative. Then at this point the slope becomes positive, phi is increasing with time, here phi is decreasing with time. So, d phi by dt is negative here, d phi by dt is positive here. So, because d phi by dt is negative here, the induced EMF is positive and induced EMF here is negative. So, the induced EMF between these two terminals keeps on changing its sign periodically with time, and so if I were to draw the induced EMF here, what will happen is it will look something like this. So, this is this point, this is this point, this is this point here. So, it will go to maximum. So, this is EMF. So, at this point rate of change of flux is 0 because the curve is horizontal, d phi by dt is 0, then d phi by dt is negative. So, EMF is positive, it becomes maximum at this point when the rate of change of d phi by rate of change of phi is maximum, slope is maximum. Then as you come to this point d phi by dt becomes again 0, and so there is no induced EMF. Beyond this point d phi by dt is positive, the flux is increasing with time, which means essentially that the induced EMF is negative and induced EMF goes like this, and this repeats itself periodically. So, this is a generator, this is a device which generates alternating EMF between these two terminals. So, half the cycle this is positive with respect to this, another half of the cycle this is positive with respect to this. So, this keeps on changing with time, and this is called an AC generator. So, if I were to draw again another figure here, so the coil will be looking like this with area pointing here, here the coil is looking like this with area pointing up, sorry down, here the coil is like this with area pointing to the left, here the coil is like this with the area, with area pointing up, and here the coil is like this with the area pointing here, and in between you will see that this has rotated like this with area going like this, here it has rotated in this direction, here it has rotated like this, and here is rotated. So, it starts from being oriented like this, then after some time it becomes like this, then it becomes like this, then it rotates to this position, then it rotates this position, then this position, then this position, then this position and this position. And as you can see here, the orientation of this area vector direction, if it was like this, the area vector is to the left, then it changes down, then it becomes to this direction, then it goes like this and then rotates. So, that is one complete cycle, and this results in induced EMF, which is changing as a function of time. So, I can actually write an equation. So, the magnetic flux phi b is b times A cos theta, where let me assume that this is my coil, this is the magnetic field direction and this is the area vector and this angle is theta. So, that is a coil, that is a side view of the coil, and this coil is rotating as a function of time. So, because the coil is rotating as a function of time, theta will be varying as a function of time, theta at any time will be omega t. It is a rotating coil. So, as a function of time, if I start from theta is equal to 0, at t is equal to 0, theta is equal to 0, as time progresses the theta keeps on changing with time, and so the magnetic flux is actually given by b times A times cos omega t. So, the induced EMF minus d phi b by dt, which is equal to minus b A omega into minus sin omega t, which is equal to b A omega sin omega t. And you can see here that this is exactly what I plotted here. At t is equal to 0, the flux is maximum. As time increases, the flux starts to decrease and the induced EMF starts to increase, because cos omega t is decreasing and sin omega t is increasing, and this is the plot of essentially cos omega t, and that is the plot the way the EMF generated varies as sin omega t. And this is why you see that the EMF is changing sign after every half a cycle, and this is precisely indicated in this figure. So, half a cycle. So, this time this is the 2 pi by omega, this is the time taken for one full cycle, which is 2 pi by omega. So, depending on the speed of rotation of this coil, the EMF cycles will be determined by that speed of rotation or angular rotation, and you get essentially an alternating EMF between these two terminals. So, in this generator, what is going to happen is, as you rotate this coil, some half the cycle this has a higher potential than this, the remaining half cycle this is at a higher potential with respect to this, and the potential difference keeps on changing with time, and this is the alternating current generator. So, this is a very important application of AC generator, where you can use induced EMF to generate alternating currents or alternating potential differences, and if you connect this to an external circuit, you can actually generate a current which is alternating current in the external circuit. So, the potential difference between this is a generated potential difference, and as you can see here, if I use mechanical energy to rotate this, I am converting mechanical energy to electrical energy through this generation process. So, I can have this rotation generated by different mechanisms. This rotation of this coil has to be done by an external agency. So, if I rotate this as a function of time, I will generate a potential difference here as a function of time, and that will be generating a current for myself. So, there are different generators. So, one is, for example, a hydroelectric generator. Hydroelectric generator, here mechanical energy falling water mechanical energy from falling water is the mechanical energy that is converted, and this can happen in, for example, dams. So, water from a height, when it falls down, it has a kinetic, it generates a kinetic energy from the potential energy, and that kinetic energy can be converted to rotation of this coil, and that it gets converted to electrical energy. Then you can have thermal generators, where water is converted first to steam, using coal or other sources. Then steam at high pressure is used for rotation. You can also have nuclear generators where you convert nuclear fuel instead of coal. And as I mentioned, the frequency of this induced EMF, that means this time period, or the frequency at which the current is changing with time, depends on the frequency of rotation of this coil, and typically in India this frequency is about 50 hertz, and in some other countries it is 60 hertz and so on. So, depending on the frequency of rotation of the coil, you will generate currents of different frequencies. Now, by a simple modification of this design, I can convert into a situation where instead of an alternating EMF, I can generate EMF in the same direction by the following arrangement. So, what I do is the following, that I have again the same two magnets, and what I do now is the coil which I am using here, the coil is like this, and what I do is the following. So, I connect this to a what I call as a split ring. So, I have so this is connected here and this is connected here. So, I must draw it to the full here. So, that is a ring here, that is another ring here, split ring, and the two contacts are taken from here. And as before, there is a magnetic field in this direction, this is north, this is south, and this entire thing is now rotating around this axis. Now, unlike the other earlier situation, what you can see here is this particular part of the ring is always in touch with the coil on the left hand side. Here what happened was the coil on the left hand side was partly connected to this point, and half a cycle is connected to the other point. So, because of this arrangement, you will find that the EMF here is not changing its sign, but it will be something like this. So, let me draw a figure again here. So, if I were to draw phi b as a function of time, suppose it is like this, just like before, this is one cycle. Let me draw the induced EMF here. So, this is 1/4 of a cycle, half a cycle, another quarter of a cycle, full cycle. So, here, so just like before, the induced EMF will first do this, and in the second part, instead of going down, it again does this, because the two terminals have interchanged themselves at the for the outside circuit, the EMF is always positive. And so, here again I will have so here the coils will be looking something like this. Here the coil was oriented like this with arrow here, then the coil became slightly rotated, then became rotated further, then it became rotated toward this side, then it became rotated to this side, then it is to this side, then it is to this side, then it is here, and finally it comes back to one full cycle. So, this coil is still rotating in the same fashion, goes from here to 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 here. But what is happening is, in this part of the cycle, the two terminals have interchanged themselves. So, instead of generating an alternating current, you are generating a current in the same direction, and so you can actually have what is called as a DC generator. So, that is the current in the same direction as always, and so you can actually modify the design of the generator to have either an AC current generated or a DC current generated. So, what we have seen is some very important applications of electromagnetic induction, and what we discussed today is one of the most important applications of electromagnetic induction in the generation of electrical current. And we can, using this principle, you can convert mechanical energy or any other form of energy to electrical energy by using the fact that when you change the magnetic flux through a circuit, then you can induce an EMF, and that EMF can be used for applications, for other applications. Okay, so with that we finish electromagnetic induction. Now I want to move on to a very important aspect of electromagnetics and introduction of what I will call as the displacement current. Now, let me try to introduce this concept through the following problem. So, let me again go back to Ampere's law. So, Ampere's law, as you know, is integral B dot dl is equal to mu 0 times I enclosed. So, if you have a current, then and if you take a loop of integration, then integral B dot dl over that loop must be equal to mu naught times the enclosed current. Now, so let me look at the following problem. So, I have a situation where I have a wire connected to a parallel plate capacitor. So, here is the capacitor plate, the second plate is somewhere here, and the wire continues to the other side. It is a parallel plate capacitor, and I want to determine the magnetic field of this. So, what I am going to do is now assume that there is a current which is changing as a function of time, that is I am charging the capacitor. So, charging the capacitor means as time progresses, this gets positively charged and that gets negatively charged. So, you have a charge potential difference, and between these two plates there will be an electric field pointing in this direction between these two plates. Now, my objective is to find out what is the magnetic field at this point. So, what I will normally do as before is take a loop like this, and so this is my loop, and here I define my, because my current is flowing like this, let me define my area loop of integration like this. Okay, so, that is a loop which I take at a distance say r from the axis, and I use this formula for calculating magnetic field. Now, if I am quite far away from this capacitor plates, for example, if I am deep inside here, then I will find that the magnetic field, because of symmetry again, has to be azimuthal parallel to this circle here at every point, and we have seen already this fact, and using this I can do an integration on the left hand side immediately and get integral B dot dl. Now, what is the current enclosed? The current enclosed is determined by, I must draw a surface for which this particular loop is a boundary, and the current enclosed is the current crossing this surface. So, given a loop of integration, I must draw a surface with this loop of integration as the boundary, and that surface, as I mentioned before, has to have this as the boundary. Now, I can choose any surface as long as I am consistently defining the enclosed current direction and the direction of integration of the loop. So, if I integrate like this, the current must be positive current is towards me, if I am integrating like this, positive current is away from me. So, depending on the direction of loop integration, the enclosed current has positive or negative sign. Now, so obviously, the first effect that you will see is why not take this surface, the flat surface which is on which the loop is lying, and in that case the current enclosed is simply the current passing through the wire. So, if I am given this loop of integration, then I will choose, I can choose a surface, one surface which I can choose is this surface which is a flat surface, and the current passing through that surface is simply I. Now, there is no requirement that I choose only this surface. For example, I can choose another surface. So, let me draw another figure here, and this figure. So, let me again draw the capacitor. So, here is the capacitor plate, here is another capacitor plate, the wire is coming from here, this wire is going away from here, and so this current is flowing in like this, and again the loop looks something like this. That is my loop. Now, there is no necessity that I must choose the flat surface. I can choose a surface which looks like this. That loop, that surface, as you can see here still, that surface has this loop as the boundary, but that surface does not intersect the wire anywhere. It passes between the capacitor plates. Please remember, in this equation, I am free to choose any surface of integration to calculate the current enclosed, the current crossing the surface. For a given loop, integral B dot dl is known, and so if I take this loop and if I take this surface of integration, which is surface cutting through the wire, I enclosed is simply the current passing through the wire. On the other hand, if I happen to choose a surface which is passing between the capacitor plates, and as the current changes, I can see that on the right hand side there is no current enclosed, because the surface is not crossing the wire at all, and this wire is beyond that point. So, this current is passing away from here. So, it looks to me that the right hand side is 0 and I get a different result. If I use this surface, I get a finite value for the right hand side. If I use this surface, I get a 0 value for the right hand side. So, there is something wrong, there is something incomplete in this equation, and this was actually discovered by Maxwell, James Clerk Maxwell, and he modified this equation by adding a very, very important term, which is what I will call as the displacement current. So, there is some incomplete, this equation seems to be incomplete, because depending on the surface which I take, I get a different value of the right hand side, and there must be a problem with this equation. So, to analyze this problem, let me take a surface which is looking like this. Okay, so, just to be a little more specific, let me take a surface. Here my current carrying wire here, current is flowing like this, flowing out, that is my loop of integration, and I take a surface which looks something like this. Okay. So, that is a surface which is a cylindrical surface which is lying like this, for example. Okay, so, between the two plates, the surface is the flat surface between the two plates, and is crossing this is crossing the area between the two plates, but it does not touch the wire. Now, let me try to calculate. So, please remember, here there is a electric field within these capacitor plates. So, let me calculate what is the electric flux through this area. Electric flux through this area, phi electric, is equal to integral E dot dA. So, let me calculate the electric flux through this entire surface, which I have now drawn, and that is given by E dot dA. So, if I neglect fringing fields in the capacitor, the field is uniform within the area between the two capacitor plates, and this simply becomes equal to E times A. Area is the area enclosed by this surface, and if this surface depending on the area. Now, what is the current that is passing through the wire? I is equal to dq by dt. Now, which is equal to epsilon 0 d phi E by dt. So, the flux is given by E times A, and so let me rewrite this equation again here. Flux is given by E times A, E is sigma by epsilon 0 into A, which is equal to q by epsilon 0. So, the electric flux is given by phi E is equal to integral E dot dA, and the flux is simply given by, because electric field is uniform, A is the area of the plates. So, E times A, and the electric field is given by sigma by epsilon 0, sigma is the surface charge density, and sigma times A is q. So, d phi E by dt is equal to 1 by epsilon dq by dt, and the current is nothing but current flowing through the wire is dq by dt. So, let me put a subscript here called conduction current, just to differentiate between another current. Remember, we have already introduced a conduction current before, a bound current, and so this is the conduction current. This is actually the current flowing through the wire because electrons are moving. So, this is I c, which is the conduction current. So, I get the fact that d phi E by dt is equal to 1 by epsilon 0 into conduction current. So, conduction current is equal to actually epsilon 0 d phi E by dt. Okay. So, if I, for example, modify the Ampere's law. So, this was the Ampere's law. So, this is usually whenever I have been discussing Ampere's law, this is current enclosed is nothing but conduction current enclosed. So, I can write this as mu 0 times conduction current enclosed. Okay. C stands for conduction current, and on the right hand side it is always the current which is enclosed, and in this case it is conduction current enclosed. Now, suppose I modify this law to the following: integral B dot dl is equal to mu naught times I c plus mu naught epsilon naught d phi E by dt. So, let me modify the Ampere's law to this. Now, you see what happens if I take a surface which is like this, which I wrote before. If this is the loop of integration and if this is the surface, then the second term is 0, there is no electric flux, and the first term gives me mu naught I c. So, if I use this on the right hand side, if I use the surface to calculate the right hand side as the flat surface containing this loop, then in this right hand side of this equation, the second term is 0 because there is no electric flux, and only the first term contributes, which is mu naught I c. On the other hand, if I take a surface which is like this, then in this case there is no conduction current, I only have the second term, and remember this term epsilon 0 d phi E by dt is exactly equal to I c. So, this term also becomes mu naught I c, exactly equal to the right hand side when I took the flat surface. So, let me repeat again. This is the loop on which I am trying to calculate the magnetic field. This is the position, and the magnetic field I know I can integrate the left hand side, and I get a value for the left hand side. The question arises as to what I choose as the surface of integration to calculate the current enclosed. So, I can choose any surface which I want. If I happen to choose the flat surface in which the current is crossing, then the right hand side is simply mu naught I enclosed, I current and I conduction, which is the first term. The second term is absent because there is no electric field flux. If I choose a surface which is like this, which does not cut the current, but it encloses the space between the two capacitor plates, then the first term in this equation is 0 and I am left only with the second term, and the second term, as you can see from here, epsilon 0 d phi E by dt is exactly equal to the conduction current that is passing through the wire. So, this equation becomes valid whether I take a surface which is in which the wire is cutting, or I take a surface in which the wire is not cutting, but I am passing through between the capacitor plates. So, this equation is more general, and this is the generalized form of Ampere's law. This term was introduced by James Clerk Maxwell in the year 1865. to 1879. He introduced modification to Ampere's law in 1865, and this term is referred to as the displacement current. This term which is coming here is called the displacement current, and that happens to be equal to conduction current in this case. So, this is called the displacement current. Is I d epsilon 0. So, this modified form of Ampere's law or generalized form becomes equal to mu naught times I c plus mu naught times I d. So, there is a conduction current term on the right hand side and there is a displacement current term on the right hand side, both together have to be taken into account in this, and this was a very major modification of the Ampere's law introduced by Maxwell, and it not only corrects the Ampere's law, as we will see that this introduces a completely different picture to electromagnetic equations, because it predicts, as I will show you later on, the existence of electromagnetic waves, the existence of waves which are just electric and magnetic fields, and light is a form of electromagnetic wave, radio waves are electromagnetic waves, gamma rays are electromagnetic waves, X-rays are electromagnetic waves. So, there is the electromagnetic waves have a very broad spectrum of wavelengths and frequencies, and the existence of electromagnetic waves came up through mathematical formulation in which Maxwell introduced this term, and this is called the displacement current. And so, because the flux is determined by area and the electric field, I can also define a displacement current density epsilon 0. This is in free space. I can define a displacement current density which is epsilon 0 d E by dt. Let me put a vector here, that is vector current density, and that is so this right hand side of the generalized Ampere's law contains conduction current and displacement current. So, depending on the situation, you may find a contribution to the right hand side because of conduction current only, or displacement current only, or both conduction and displacement currents. So, it is possible in situations where there is a conduction current and there is also a displacement current, both of them contribute to the generation of magnetic field. Now, what is very significant is the fact that this term is a very important term in the following sense. Suppose I have a situation where there is no conduction current, a situation where there is no conduction current, then according to Maxwell's equation, integral B dot dl, because of the modification, I have mu naught epsilon naught d phi E by dt. that is the displacement current, and I am assuming that I am taking a region where there is no conduction current. Look at the other equation, integral E dot dl minus, this is the Faraday's law. A changing magnetic flux induces an electric field, a changing electric flux induces a magnetic field. Faraday's law of induction tells me a changing magnetic flux induces an electric field in space, a changing electric flux induces a magnetic field in space. So, this term actually makes the electric and magnetic fields coupled to each other and symmetrizes the equations. Symmetry is very beautiful, but here what is happening is essentially that changing magnetic flux generates electric field, a changing electric flux generates magnetic field. So, this term actually symmetrizes the equations, electromagnetic equations, and we will see later on when we start to discuss electromagnetic waves that this term actually predicts the existence of waves. Now, let me take an example. An example I want to consider is a parallel plate capacitor. With circular plates of radii r, and capacitor is getting charged. So, let me draw the two capacitor plates. So, that is one plate here, another plate, and so current is flowing like this, and this is accumulating positive charge here, and this is accumulating negative charge here, and there is an electric field between these two. Now, I want to calculate. So, this tells me, this equation tells me that the changing electric flux generates a magnetic field. So, I want to calculate. So, according to this equation, because when I am charging the capacitor, if I varies with time, I am charging the capacitor, the charge on the capacitor varies with time, sigma varies with time. If sigma varies with time, electric field varies with time, and if electric field varies with time, the electric flux through any closed surface, through any surface, not closed surface, any surface will vary with time. If I take a surface like this, the electric flux with this through this surface will vary with time, and that should induce a magnetic field according to this equation, because if the flux changes, if the electric flux changes, I should have a magnetic field. So, let me try to calculate the magnetic field between the plates of a capacitor generated by the changing electric field. Now, so in this case, if I take this loop here, and if I apply this equation, integral B dot dl is equal to, now I had this general equation which was mu 0 times I c plus mu 0 epsilon 0 d phi E by dt. Now, for this surface there is no conduction current. So, this becomes equal to mu naught epsilon 0 d phi E by dt. Now, because the plates are circular, there is circular symmetry, there is no variation with this direction, with this distance here between the two plates, the electric field is uniform, and so the magnetic field will have only an azimuthal component. It cannot have a radial component because of the magnetic flux, total flux through any closed surface being 0. There cannot be radial magnetic field, there must be an azimuthal magnetic field. So, the magnetic field must be pointing azimuthally like this. So, let me use this argument to calculate the magnetic field. So, first thing is, what is the electric flux? Phi E is equal to the electric field into this area. So, let me take an area radius r. So, electric field into area, which is equal to sigma by epsilon 0 into pi r square. And what is sigma? if the area of the plates is so the area of the plates have a radius r. So, area is equal to pi r square. So, this is equal to, so this is equal to q by pi r square epsilon 0 into pi r square, which is equal to q r square by epsilon 0 r square. So, that is the electrical flux passing through this. So, rate of change of flux d phi e by dt is equal to r square by epsilon 0 r square dq by dt, and dq by dt is nothing but the current that is charging the capacitor. So, this is r square by epsilon 0 r square into I. So, the rate of change of flux through this loop, small r I am assuming to be less than capital R. That means, I am taking a loop within the capacitor plates and smaller radius than the radius of the capacitor plates itself. So, I get d phi e by dt is this thing, and integral b dot dl. Now, as I mentioned, because of symmetry, the magnetic field will have to be azimuthal, and if I calculate the b dot dl, I will get 2 pi r times b. Please note that I must take the correct direction. If the electric field is pointing to the right and I am integrating the flux as a positive quantity, which means the area vector of the area is pointing to the right here, which means that the direction of the magnetic field must be like this, and so I get an equation. So, if I use this equation, b dot dl is equal to mu 0 epsilon 0 d phi e by dt. This gives me 2 pi r times b is equal to mu naught epsilon naught into d phi e by dt. I just now calculated r square by epsilon 0 r square into I, which is, so b is equal to, so epsilon 0 goes off, and so I get mu naught I by 2 pi r square into r. So, one of the r cancels off and I get mu naught I r by 2 pi r square. So, magnetic field within the area of the plates increases with small r. That means, at the axis the magnetic field is 0, and as you increase small r up to capital R, this will be the magnetic field. So, this is r lying between 0 and r. Similarly, I can calculate the magnetic field outside the plates of the capacitor. So, if I draw the figure again, I have the capacitor plate like this. Now, my loop is outside the place of the capacitor, but the electric field is only in this region. The electric field only exists in this region. So, phi e, the electrical flux becomes phi e is equal to E into pi r square. Although this radius is small r, there is only flux up to capital R. So, this is equal to sigma by epsilon 0 pi r square, which is equal to q by epsilon 0, because pi r square is the area of the plates, sigma is the charge density, and so d phi e by dt is 1 by epsilon 0 dq by dt, which is 1 by epsilon 0 I. So, if I again use the fact that the magnetic field is azimuthal, then I will get 2 pi r into b is equal to mu 0 epsilon 0 into I by epsilon 0. So, b is equal to mu naught I by 2 pi r. This is for r greater than capital R. So, if I were to draw the magnetic field as a function of distance, and this is capital R, the magnetic field increases and then decreases, and at this point the magnetic field is mu naught I. So, what we have seen is there is a magnetic field generated between the capacitor plates, when the current is when the capacitor is charging. Once the charging is over, once the current has become constant, the rate of change of flux on the right hand side is 0. There is no conduction current through this area, there is no d phi by dt. So, there is no magnetic field, magnetic field becomes 0. So, magnetic field is generated as long as the current is flowing in this region here, or it is actually the flux is changing with time. So, there is no change of flux, and so the magnetic field there is no magnetic field generated by changing flux. So, I will discuss further examples in the next class, and we will then move on to a very important aspect of electromagnetic waves, that is electromagnetic waves, and how these equations predict the existence of waves which are the electromagnetic waves. Thank you very much.